Mr. Dean. This time we're talking functions, a very important idea in mathematics. Not this type of function, nope. Not this type of dysfunction, nope. Not this type of family dysfunction. We're talking about mathematical functions. Let's say I walk up to a good old calculator machine and I press a 3 and out comes a 5. And the next time I press a 4 and out comes a 7. Maybe I press a -1 and out comes a 0. And then I press the 3 again, and this time out comes, well, 5. And I walk over to another different Coca-Cola machine, and we go, let's say, this time input is 2, output is 2. Our input is -1, maybe we get a 3. We press a 7, out comes a 5. We press an 8, out comes a 5. We press a 9, out comes a 5. And maybe we press a 2, and out comes a 3. Which one of these machines is not a function? Which one of these is not a function? Take a moment and think about it. Is it the one on the left or the one on the right? It is the one on the right. The one on the left is a function. Let's talk about that for a moment. All right? It is okay that this happens. All right? In fact, that's good. For every input, there should be only one output. And if you have the same input, you should get the same output. So if you go to a Coke machine and you press 3, which might be a Sprite, you hope that every time you press 3, you get a Sprite. Now, what's the matter with the machine on the right? Well, this is not the problem. Some machines will have more than one button to get out, say, your Diet Coke or something. So you could press 3 different buttons and get out the same thing. That's okay. What happened here, that was the problem, was you pressed a 2 and got out a 3, because earlier you pressed a 2 and got out a 2. Not a function. Every input must match one output. In function notation, we write it with this f in the parentheses x. It does not mean multiply. We talk about it as f of x or f at x. And we have inputs or our domains. Those are the same ideas. And those are our x's usually. And our outputs and our ranges, those are designated with a y often enough. Okay? So here's an example where we got the Dasani machine. You got all sorts of waters, but it is a function because it doesn't matter which button you press, you know you got to get what you're going to get. It's not like sometimes you press the blue 0 button and all of a sudden you get out, something totally different. Just think about numbers. We'll take a look at let's just cut this down. We'll just look at the top row here. Is this a function over here on the left, number 1? It sure is. 1 becomes 1, 2, I got that. Taking a look over here, is it okay that this happens? Inputs on the left, outputs on the right. No, because when you press a 3, you get out a 3 or a 4. No good. Is this okay? Number 3. You press a 3 or a 4 and got out a 4. Yes, that is a function. Every input on the left gets only one output on the right, so that's okay. And then looking over here, and the last one, the 1 becomes a negative. That's no good, so that's definitely a no. Next, talking about domain and range. This is a topic that we'll use for the rest of the year, so we'll get used to it here. The domain is all the numbers allowed to be entered into a function, basically. And you'll get some kind of outputs. All right? When would you not get an output? When you divide by 0 is a big one. All right? Or maybe you're taking a square root of a negative. Those are the two big problems with domains. The domain of most functions, though, is all real numbers. All right? So usually it's not a problem. So you got this big old polynomial here. The domain's all real numbers. And the way to write that in our function notation is -infinity to infinity with a comma in between. Now there are 2 types of equations, as I spoke of, that'll have more interesting domains. All right? And here's some examples. These are really important to write down. Example 1, f of x equals a fraction, 2 over x minus 3. Well, that denominator here, cannot be equal to 0. So we cannot have a 3 in for x, because if we do, we'll be dividing by 0. So the way we write it in integral notation is that our domain goes from -infinity to 3 with a union of 3 to infinity. If you think about the number line, right, here's your number line, we'll put 0 on it. The numbers that can go into this function here in example 1 basically every number except for 3. We want to skip over 3, skip it over like that. And we want everything past 3 on the positive side as well. So that's the way we write that there. Now with fractions, the range, the numerator is just, it's not a variable, it's just a constant, it's 2. So that means it's interesting that this fraction can never equal 0. And so that's why we have our range go from negative infinity to 0, and then 0 to infinity. And the u just kind of means and, put together. So on the left here, we have another example. First one was a fraction. The next one is I don't know if you can see it, it's a square root. Square roots are a special example also because roots have to be greater than or equal to 0. All right? Roots have to be greater than or equal to 0. They can't be negative. So we find out when would 2x minus 5 be negative? And we found out that if x is greater than or equal to 5 halves, then we'll be okay. It'll be 0 or positive. So our domain is going to look a little different. It's going to start at 5 halves with a sharp bracket here. Get rid of that so you can see. We'll explain it in a second. Go all the way up to infinity. And our range will just be positive numbers because square roots have to be positive. The answer to a square root has to be positive. So these sharp brackets and all that, what does it mean? Interval notation. Parentheses here mean not including. All right? If you think of them as hugs, it's not a very tight hug, whereas these brackets are tight hugs, and you want to include that number. All right, we always start on the left, the minimum number, and go to the right, the maximum number. And you can actually have a combination of a hug. It means include this number, but don't include that number on the right. So now we can do some fancy talk, fancy problems. We're going to determine the open intervals, intervals on which the function is increasing or decreasing. The open intervals on which the function is increasing or decreasing. I'm going to write our answer in interval notation. So here's our fancy, looks like a third-degree polynomial. Here's the graph over on the right. We have our local maximum. Local just means within our graph, because of course the maximum, this just goes up forever, so our maximum would be considered infinity. We have our local minimum, which is just, again, locally on the graph that we're looking at, although in the big picture it goes down to negative infinity. And the open intervals in which the function is increasing or decreasing, we're going to be reporting the x values here. So I see that it is increasing. This is increasing. This value is increasing from negative infinity all the way up to about there, which looks roughly about negative 2, but maybe it's negative 1 or something like that. Negative 1. All right? Now, we always use a parenthesis around infinity and negative infinity. We never include it because it's not really a number you can stop at. Now, we're going to continue on increasing, but we're not going to increase until we get past our local minimum, which, I don't know, looks like about, we'll roughly say 1. I know it's not exactly 1. And that increases up forever. All right? So the increase is from here to here, and then it's also increasing there. So that's why we have our u. Now it's also decreasing in this little section here. All right? And so for argument's sake, just to show the example, it's decreasing from x equals negative 1 to positive 1. All right? I'm not worried about the y values. I'm just reporting the x values when we talk about open intervals. Next off is piecewise notation, and this gives people's fits. Basically what it is just kind of 2 problems, or maybe even 3 or 4. This one is 2. Think of them as separate problems, and we're going to graph 1 minus x, all right? And the location we're going to graph it is x is less than negative 4, less than or equal to positive 4. So let me graph 1 minus x, first of all. We have a y-intercept there, and go through there. All right, that's roughly it. Continue on there. But I only want to have that graphed for x is less than or equal to 4. So I'm going to go over here to 4, right there, go down to where my graph is, and then anything past that, I do not want to include that. I want to include it at 4, so I'm going to put a dot. So the graph ends there and goes in the left-hand direction forever. Put a sloppy little arrow there. All right, that's all it is. The next one we're going to also graph on the same set of axes. This time it's 2x minus 6. So I'll graph that, go up to and over 1, and right there. And I want it to only exist if x is greater than 4. Well, then I really didn't need to write all this, but I don't mind writing it because it makes some sense to me. So we'll fix that in a moment. And I don't want to include 4 because there's not a, it's just a greater than 4, it's not equal to 4, so we'll put an empty hole there. And then I'll just fix that part there a little bit. So that is what our graph will look like there. The arrows on the end, probably should put them there as well. All right, so anyways, if they ask some questions like what's the value of f at 1, all right, let me erase all this. This function is just one function that has two parts. F at 1, well, 1 is not greater than 4, so we're not going to use that bottom equation. We're going to use the top equation. And it looks like once I put 1 in there, I'll get out 0. F at 4, well, 4 is not greater than 4. I'm not going to use the bottom equation. All right, these tell you which equation to use. 4 is equal to 4, so I'm going to use this equation, 1 minus 4, negative 3. And if I even looked at my graph, if I went over to 4 and I looked down, my value would be negative 3. So that is showing the same information on the graph. If f is 0, I would have 1. So I would still use that same top graph. All right. How to do piecewise on a calculator? There's a piecewise equation on a calculator. It's pretty simple. Let me go to what it looks like. I put parentheses around, in this case I had 2x minus 4. So I had 2x minus 4, and I wanted that to only exist for x is greater than negative 2. And then I had another part of my equation be negative x, and that's all. And then I had, if I can arrow over, x was going to be less than or equal to negative 2. All right, and you can see on the calculator, or if you have a smartphone, you might not be able to see it. Everything's in parentheses. All right, so on the calculator, I would sort of need to have parentheses around this, parentheses around this, around this, around this, around this, around this, parentheses everywhere. All right, continuing on, domain and range if you have a graph. The domain is the x-axis, remember, and it looks like the x's go negative infinity, and they stop at 5. And they include 5, never include infinity. The range is the y, so think of it in the up and down sort of sense. And that starts, this graph down here, it goes forever down the negative direction and goes up until 2. Stops at 2 and it's going to include 2. Okay? So that's how to do it, domain and range for a graph. Sometimes that can be a little tricky. Remember, friends don't let friends divide by 0. That's a basic fact. And there's some things in the textbook you might want to just check out because there's a couple details here and there, but that pretty much wraps it up. You've been great, audience. We'll see you in class.